Have you ever wondered how many times aluminum can be recycled? Imagine this. One can you drank from today could be back on the shelf as a brand new can in just 60 days. And here's a jaw-dropper. Over 120,000 aluminum cans are used every minute worldwide. But wait, there's more. In the United States alone, enough cans are recycled each year to cover 3,000 football fields. Why is recycling aluminum so critical? How do these tiny metal heroes make such a massive impact on the planet? Let's dive into this video where every statistic amazes, and the transformation process will leave you inspired. The journey of recycling aluminum cans starts with collection, a crucial step in the recycling chain because timely gathering of raw materials ensures efficient processing later on. Most aluminum cans are collected through specialized waste collection systems in cities and communities. Many countries have waste sorting programs encouraging consumers to deposit empty cans in dedicated metal recycling bins. In the United States, there are widespread redemption centers where consumers can return used cans for a small cash reward or discount, incentivizing eco-friendly behavior. These programs are also common in parts of Europe and Australia. Some regions even organize campaigns where individuals can bring used cans to special recycling stations, making it easier to gather metal waste while reducing environmental pollution. Globally, about 120,000 aluminum cans are used every single minute, a staggering number that highlights the importance of efficient recycling. Many stores feature special bins for collecting empty aluminum cans, especially in areas with popular deposit systems where consumers can return packaging for a refund, often earning a few cents for each can. Beverage manufacturers and packaging companies also participate in the recycling process by sending metal waste from production to collection centers. This applies to used cans and leftover aluminum elements from the manufacturing process. Some recycling systems even include automatic waste sorting at the collection stage. Advanced technologies like magnetic separators are used to extract aluminum from other metals and plastics efficiently. In regions without such systems, manual sorting is still the norm. In the United States, the aluminum can recycling market is valued at over $1 billion annually. This massive industry injects revenue back into the economy, fueling businesses that recycle and produce new products from repurposed metal. Once collected and sorted, the cans are transported to a recycling facility, where they're stored in massive containers or warehouses until processing begins. The entire recycling journey of an aluminum can take less than 60 days, from the moment it arrives at the facility to the moment it's transformed into a brand new product. That means the can you finished today could be back on the shelf in just 2 months. To ensure a smooth process, cans must be kept separate from other waste materials, so they're often stored separately. Before moving on to further processing, the cans undergo a thorough cleaning. This includes washing off any leftover liquids, removing labels, adhesives, and other contaminants that might still be on the packaging. And now for the most epic part, shredding. Once cleaned, the cans are shredded into small pieces using industrial shredders or other mechanical equipment. This step drastically reduces the volume of the material, making it easier to process. What's left are aluminum shreds, or chunks, ready to be transformed into new products. I've got to say, being there for this part was nerve-wracking. It felt like one of those shards might fly off and hit me in the eye. And the noise, the grinding and crunching were absolutely deafening. Hot. Insanely, blisteringly hot. That's how it felt when we approached the smelting furnace. The shredded aluminum pieces are sent straight into it. 1,220 degrees Fahrenheit, a temperature so intense, it's surprising it's not 1,222 for some devilish symmetry. Melting is the key stage where the metal is heated until it turns liquid. During this process, any remaining impurities and other materials are burned away, leaving behind pure aluminum ready for reuse. Watching it felt like witnessing the Terminator's final moments. I swear. The team explained to me that smelting is energy intensive, but even with the high energy consumption, this process is far more efficient and less costly than extracting virgin aluminum from ore. The molten aluminum from the furnace is poured into molds to create ingots, wire rods, or sheet metal. These aluminum ingots, known as slabs, are massive blocks that are easy to handle during later processing stages. Each slab measures several yards in length and about 2 feet thick. Once cooled and solidified, this metal is ready for a new life, whether as fresh aluminum cans, car parts, construction materials, or other products. Here's the incredible part. This process can be repeated endlessly. Aluminum can be recycled over and over without losing its quality. Imagine that. Cans can go through the recycling loop dozens, even hundreds of times. It doesn't wear out from remelting. Honestly, it feels like we were lied to. Terminator had to be made of aluminum, folks. Now, what are these wire rods, you ask? Fair question, and I've got the answer for you. Wire rods are a form of aluminum created after the molten metal is poured and shaped into thin wires or rods. After smelting, the liquid aluminum is cast into molds for further processing. The metal is rolled into large wire rods using specialized rolling mills. These mills reduce the cross-section of the metal and shape it into the desired form by passing it through rollers. The rods can then be cut into smaller sections or sent off for additional processing to create a variety of aluminum products. In the end, wire rods are the foundational form of aluminum used to manufacture new products. This keeps the recycling and reuse cycle going strong. The diameter of aluminum rods can vary depending on their intended purpose, typically ranging from 0.04 of an inch to 0.75 of an inch. However, this can change based on production specifications and the final application. Thin wire rods, with a diameter ranging from 0.04 to 1/10 of an inch, are commonly used to make wires, electrical cables, or delicate metal components. Medium wire rods, measuring 1/16 to 0.4 of an inch, are suitable for sturdier products like structural elements, or, in some cases, new aluminum cans, when further processing requires that specific diameter. Thick wire rods, over 0.4 of an inch in diameter, are reserved for heavy-duty applications such as the automotive industry or the production of large structural components. Each type of wire rod has its own specifications and undergoes additional processing depending on the final aluminum product being manufactured. To produce aluminum sheets, the slabs are gently heated and passed through powerful rolling mills that flatten them into thin sheets. At this stage, the sheets measure about 1/4 to 2/5 of an inch thick, but they're still too thick for most applications. After hot rolling, the sheets are cooled to stabilize their structure. If needed, they undergo annealing, a controlled process of heating and slow cooling, to relieve internal stress and improve the metal's flexibility. For ultra-thin sheets, like foil or packaging materials, the aluminum goes through cold rolling, reducing its thickness to less than 0.04 of an inch. This precision ensures the sheets meet the requirements for various specialized applications. Once the aluminum is formed into the required shape, whether as wire rods or sheets, it's transported to factories or directly to customers for further use in manufacturing. Recycling aluminum requires significantly less energy compared to extracting new material from ore. In fact, recycling aluminum saves up to 95% of the energy that would otherwise be needed for mining and processing raw aluminum. To put it into perspective, it's like a 100-watt light bulb running for 4 hours. Here's another mind-blowing stat. If all the aluminum cans recycled in the United States each year were stacked end-to-end, they'd cover approximately 3,000 football fields. And if you combined the recycled cans from the US and Europe, they could wrap around the Earth twice. You wouldn't believe how much technology goes into making ordinary toilet paper. Robots cutting trees with laser precision, machines rolling them out at speeds of hundreds of miles per hour, and even artificial intelligence monitoring every single inch for quality. After this video, you'll never look at toilet paper the same way again. Watch till the end. It's going to blow your mind. Let's dive right in. The process starts at logging sites, where machines known as harvesters are used. These impressive machines cut down trees, strip them of branches, and chop them into logs of precise lengths, all in one go. Honestly, I could use something this multifunctional for cleaning my house. Logging is meticulously planned, using GPS and GIS to identify optimal areas for cutting while adhering to strict environmental standards. Trees are harvested selectively to prevent over-deforestation. Logs are then transported to pulp mills by specialized trucks equipped with GPS trackers that optimize delivery routes. Alongside fresh wood, these factories also use recycled paper, collected through recycling programs, delivered as compacted bales. At the mills, the logs are fed into automated lines, where they're chipped into small, uniform pieces. See how tiny these chips are? That's thanks to industrial-grade chipping machines, equipped with sensors to control wood size. These chips are moved along automated conveyors to massive digesters. Before entering the digester, the chips pass through magnetic separators to remove any metal and sieves that ensure uniform size. Sensors and computer systems manage every stage. Inside the digester, the chips are mixed with chemical solutions like caustic soda and sulfides, a process called the Kraft method. Automated dispensers precisely measure and add chemicals based on the type of wood being processed. Feeling the heat yet? Inside the digester, the chips are heated under high pressure for several hours. This entire process is automated. Computer systems carefully control temperature, pressure, and cooking time to produce the perfect consistency of pulp, a mixture of solid particles and liquid. Now, check this out. The pulp is pumped into centrifuges, which remove heavy impurities like stones, sand, or metal. Chemicals are then added to break down any remaining linin, the substance that binds wood cells together. Advanced sensors monitor temperature, pressure, and chemical concentrations to achieve optimal pulp brightness without wasting reagents. After this, the pulp is washed to remove residual chemicals and byproducts. Multi-stage washing systems clean and recycle water, minimizing waste. Oh, you're still here? Great. Quick story. One Halloween, I was completely swamped with deadlines. Instead of competing in our neighborhood's annual Best Holiday Decorations contest, I gave up. In a moment of pure laziness, I TP'd my own house, just like in those classic prankster movies. Surprisingly, it got more compliments than any decor I'd ever done. The irony, right? Anyway, back to business. Once purified and bleached, the pulp, which now has a creamy consistency, is piped to forming machines. Sensors installed in these pipes monitor temperature, moisture levels, and pulp density. The pulp is spread onto a forming table, the core component of the paper-making machine. This section consists of an endless wire mesh, moving at speeds of up to 63 miles per hour. The pulp is evenly distributed onto the mesh through nozzles, and excess water is removed immediately using vacuum pumps. The sheet then moves to the press section, where special rollers covered with silicone or rubber squeeze out more moisture. Next up, drying. The sheet passes through a giant cylinder known as the Yankee dryer, heated to temperatures between 240 and 300 degrees Fahrenheit. By the end of this stage, the paper's moisture level drops to around 5%. Sensors constantly monitor the cylinder's temperature and rotation speed to prevent overheating or overdrying. Now for the finishing touches. The dried sheet undergoes embossing, where textured patterns are pressed onto its surface. This step enhances the paper's softness, absorbency, and appearance. Steel or rubber rollers with intricate designs create these patterns. Automated systems ensure the patterns are crisp and evenly applied. Some manufacturers add fragrances or moisturizing agents at this stage, spraying them on in thin layers using advanced nozzles. Optical and ultrasonic scanners monitor parameters like thickness, density, and uniformity. If defects such as tears or uneven textures are detected, the system automatically adjusts or discards the flawed section. Data from all scanners is fed into a central computer, analyzing the entire line's performance in real time. It can even predict potential issues, like roller wear, and notify operators for maintenance. Cool, right? After forming and drying, the paper is rolled into massive jumbo rolls. These rolls can measure several feet wide and weigh hundreds of pounds. Robotic arms transport the jumbo rolls to the rewinding section, where the sheet is unrolled, smoothed, and prepped for cutting. Rewinding machines stretch the paper and roll it onto cardboard cores, which are automatically fed into the line. Check this out. These machines can wind hundreds of rolls per minute, and they're constantly monitored for tension or defects. If something's off, the system pauses to prevent waste. Once rewound, the rolls move to the cutting section. Here, larger rolls are sliced into smaller, standard-sized rolls using high-speed cutting machines. Titanium or steel-coated blades ensure clean, precise cuts without damaging the paper. These machines operate with millimeter precision, guaranteeing uniformity. Automated systems monitor blade sharpness, replacing dull blades without interrupting the process. Each roll undergoes final inspections via high-resolution cameras and infrared sensors, checking diameter, density, and cut quality. Defective rolls are swiftly removed using pneumatic arms. Finally, the finished rolls head to the packaging section. Robotic systems handle them without contact, reducing contamination risks. Sensors align the rolls before they enter the wrapping machine, while a computer system ensures all rolls meet size and weight standards. The rolls are grouped into packs, 4, 6, 12, or even 24, based on consumer demand. Robotic arms stack and wrap the rolls using either thin but durable plastic film or eco-friendly paper packaging. This ensures protection from moisture and dirt while catering to environmentally conscious buyers. What do a sandwich, potato wedges, and pasta have in common? That's right, cheese. It takes these simple dishes and turns them into pure bliss. There are plenty of cheeses in the world, but cheddar holds a special place in my heart. Today we're diving into my love story with this cheese, my go-to for the easiest, most delicious meals I know. Let's get started. At the cheese factory where cheddar is made, pasteurization is like a technological dance. By the way, are you into techno? The process kicks off with an automated system moving milk through a network of sterile pipes to a pasteurization unit. Here, heat exchangers warm the milk to an exact temperature, typically between 161 and 167 degrees Fahrenheit. It's not just heating, it's a precision process that destroys harmful microorganisms while keeping the milk's nutrients intact. The secret lies in the control system. High-precision sensors continuously monitor the milk's temperature. Once the milk has been heated for the required time, it's cooled down almost instantly to a safe 39 degrees Fahrenheit. Here's where it gets innovative. The heat released during cooling is reused to warm the next batch of milk. This energy regeneration is both cost-effective and eco-friendly, reducing the production's overall energy consumption. In the warm halls of the cheese factory, where the milk has already been pasteurized, the next step begins, adding the starter culture and rennet. The pasteurized milk is poured into large stainless steel vats, where it's heated to around 86 to 89 degrees Fahrenheit, the perfect temperature for the starter culture to do its magic. A computer system controls every detail, from the milk volume to the exact temperature in each vat. The starter culture goes in first. These are carefully selected lactic acid bacteria that give cheddar its signature flavor and texture. Delivered as either a powder or liquid, the culture is measured precisely by robotic dispensers. Once added, large mechanical paddles gently stir the milk, ensuring the bacteria are evenly distributed. Next comes the addition of rennet, a microbiological enzyme called renin. It's eco-friendly and even suitable for vegetarians. Adding rennet is where the magic happens. It transforms the milk into a curd in less than an hour, laying the foundation for cheddar. While the rennet works its magic, the system keeps an eye on every change in the milk. Sensors measure acidity and density, while algorithms determine the exact moment to end this phase. Modern technology ensures the process is quick, efficient, and requires minimal human intervention. Once the curd is fully formed, the milk is no longer a liquid. It has become a smooth, tender cheese mass ready for the next step in becoming the famous cheddar. Cheddar is the reason I took my first steps in cooking. Actually, I've taken a lot of steps since then, but I still feel like I'm standing in the same spot. But let's not talk about that. Let's talk about 10-year-old me trying to cook for the first time. Picture this. Me, a heated pan. My mom watching from the corner of the kitchen, ready to call 911 if needed. And there they were. 2 slices of bread slathered with butter and a generous slice of cheddar. Sure, the bread got a little burnt, but it still tasted incredible. By the way, what was the first thing you ever cooked? Forming the curd is when cheddar starts to take physical shape. Every parameter, temperature, acidity level, enzyme timing, is carefully monitored. Sensors continuously measure the milk's density to determine when the curd has reached the ideal consistency, which takes about 30 to 40 minutes. Look at this giant vat. The milk seems to have frozen in time, turning into a soft, gel-like curd. Once the sensors confirm the curd's structure, special knives come into play. These are automated paddles fitted with blades that gently cut the curd into small cubes. They move slowly and evenly to maintain uniformity, which is essential for separating the whey later. At the same time, the vat is gradually heated to around 100 to 104 degrees Fahrenheit. This secondary heating helps expel whey and solidify the cheese granules. As the whey separates during heating, it's drained through special valves at the bottom of the vat. This process is also automated, ensuring just the right amount of whey is left to maintain the cheese mass's proper consistency. What remains in the vat is dense yet tender curd, ready for the cheddaring process. You've been waiting for this part, haven't you? The curd, now formed into large chunks, is transferred to special tables or conveyor belts made of stainless steel with built-in heating systems to maintain the optimal cheddaring temperature of around 95 to 100 degrees Fahrenheit. The curd is stacked into layers, distributed evenly by robotic manipulators or conveyor systems. These layers rest for a specific time, allowing them to bond and compress. Under its own weight and the steady temperature, the curd releases residual whey. After a certain period, the layers are flipped over. A key feature of the cheddaring process is the gradual acidification of the curd. This happens thanks to the lactic acid bacteria added earlier with the starter culture. Their activity alters the cheese's chemical composition, giving it a mild, slightly tangy flavor. By the time cheddaring is complete, the curd becomes dense, elastic, and ready for the next step, cutting and salting. Automated cutting systems divide the curd into equal pieces, ensuring consistent weight and size for every portion. At this point, my friend, we're one step closer to achieving cheddar's authentic flavor and texture. Now the curd, firm and springy, moves along specialized conveyors. Come closer and take a look. This is where the curd is cut into blocks or cubes, depending on the intended product. Next, it's time for salting. In the US, 2 main salting methods are used: brine baths and dry salting. The choice depends on the recipe for each batch of cheddar. In brine baths, large tanks are filled with a salt solution, where the cheese is submerged for several hours to allow the salt to penetrate its structure. For dry salting, the cheese blocks travel along a conveyor, passing through machines that evenly sprinkle salt over them. Salt serves a dual purpose. It enhances flavor and acts as a natural preservative, protecting the cheese from unwanted microorganisms. During this stage, the cheese continues to release residual whey, which automated systems collect and process for further use or recycling. And now, it's time for aging. This, by the way, is something I have zero patience for when it comes to cheddar. The cheese blocks are sent to special aging rooms, also known as maturation chambers. These chambers are equipped with modern climate control systems that automatically maintain optimal conditions for cheddar to age. Temperature, humidity, and air circulation are regulated with precision, down to the 10th of a degree or percentage, because even the slightest deviation can impact the cheese's quality. Cheddar is typically aged anywhere from a few months to several years. Young cheddar has a mild, creamy taste, while aged cheddar develops a rich, tangy flavor with a crystalline texture. The aging duration is determined during the batch planning stage, and all parameters are recorded in a centralized computer system. Robotic manipulators carefully stack the cheese blocks on racks in the aging chambers. These robots are programmed to minimize contact with the product, ensuring a high level of hygiene. The rack systems are also automated, capable of rotating or moving the blocks for even aging. Throughout the aging process, the cheese is closely monitored. Automatic sensors in the chambers continuously check the microclimate and even analyze gases released by the cheese to track chemical changes in its structure. In some cases, cheddar is coated with a layer of wax or a special film to protect it from drying out and environmental exposure. For aged varieties, dry aging is sometimes used, leaving the cheese uncovered to form a natural rind. When this method is chosen, automated systems periodically move and flip the blocks, cleaning them of any accumulated dust or mold.